Hey guys, how are you today? In the last video, we have seen the difference between virtual machine and container and how container is lightweight and it provides isolation that we need just like a virtual machine. In this video, we are going to take a slightly deeper look and understand how container isolation is possible, how this is actually working behind the scene. So let's get straight into it. The container isolation works by using two important concepts from Linux. The first one is called namespace and the second one is called C groups, or this is also known as control groups. So these are the two important concepts from Linux that makes container isolation possible. So now let's understand how these two helps us to create this isolation. Now when we run a container, what we expect is we expect the container to be isolated from the host operating system. We'll have host operating system and we want our container to be isolated from the processes that we see within the host operating system and also the processes running in the other containers. So if this host operating system has multiple containers, say container A and container B, if each of these have their own processes, let's say for example container A has process 1 and process 2 and container B has process 3 and process 4, then we don't want process 1 and 2 to see process 2 and 3 and also any other process running within a host operating system. And similarly, container B's process like process 3 and 4 should not see process P1 and P2 from container A. So that is the type of isolation we need. And in addition to this, process 1 should be able to see process 2 because they both are running in the same container. Similarly, process 4 should be able to see process 3 and vice versa because they are running in the same container. So process running within the same container should be able to see each other, but they should not be able to see process in other containers as well as the host operating system's process. But host operating system should be able to see all of these processes. Okay, so this is made possible by one of a namespace within Linux called PID namespace, PID namespace. What this allows us to do is when a process is created, we can map this process to a namespace. So what we typically do is when a container is created, we'll create a PID namespace for that container and all the process that are spawned inside that particular container will use the same namespace. And these namespaces will be unique among containers. So each container will have their own unique namespace. This way, the process that are running within a container will be able to see other processes running within the same container, but they'll not be able to see processes from other containers. Okay, but host operating system being the king, it will be able to see all the process whether it is running inside a container or not. So this is the first level of isolation layer at process level. But this is not enough, right? We need more. So now we have isolated the process, but we need more. What else we need? We need a different file system, right? So when host operating system has its own file system, we don't want to use our container to use the same file system. Otherwise, it affects the isolation that we need, right? I mean, what is the point of having process isolation, but at file level, they are sharing the same file system? It doesn't provide the isolation that we need, right? We also need isolation at file system level. And for that, we use another namespace from Linux called mount namespace. And this mount namespace allows us to create this file system isolation. So what happens behind the scene is when a container is started, then within that container, we mount a particular path from the host as a root. So within a host, for example, we may have a location called something like XYZ. This path will be mapped to root within the container. So this will be in host and this will be within a container. So in host, this will be this path, but within a container, it will be root. So this is the file space isolation we create. So basically we mount one of the path in the host as a root within the container. So host will be able to see what is going on in that particular path, but from container perspective, it will think that this is its root. So this path is the root of that particular operating system, and it will go and create file systems for Linux as it would normally do. Okay, and container will not be able to do anything outside of this path. Okay, so it can't go one level up or anything like that to look at the host operating system's file system. Its access is restricted to this particular path, and this path is mounted as root within the container. Okay, now we have achieved process isolation. We also achieved file system isolation. What other isolations we need? We need network isolation, right? For network isolation, we use net namespace. Net namespace allows us to create a independent network for the Docker containers or the containers. Okay, so that is net namespace. Then we also have some additional useful namespaces like UTC. UTC is now it is kind of a misnamed namespace, but it means Unix time sharing, but what it actually represents is the host name. So we can have host name for our container by using this UTS namespace. Then we also have IPC namespace. IPC namespace is for inter-process communication. So when a process is running within a container, the process which are within the same container should be able to communicate with each other. And a standard way to enable communication between processes is using shared memory and some other message processing system, okay, within Linux. So what we want to do is, we still want to enable inter-process communication among the processes running within a container, but we need to make sure it doesn't impact or affect processes running in other containers or in the host operating system. So that is the isolation we get from this IPC namespace. Okay, and there are two other namespaces. One of them is user namespace. User namespace is not enabled by default with the Docker. This allows us to map a user within a container to some other user outside of the container. So we may have user A within a container and we want to map that to user B in a host. Then we will be able to do that sort of mapping with the user namespace, but by default this is not enabled. By default we will not have this mapping. The container will run as root, and if somehow we have container escape, then that user will be able to, if somehow somebody who is using a container escapes the container and reaches the host operating system, then they have full access, because the container is running as a root. So if a user using the container as root is escaping the container somehow and reaches the host operating system, then they have full power on the host operating system. So this is one of the security issue, and for this the modern option is to use rootless container. That is a different topic altogether. I don't want to go into that, but for this video let's focus on the fact that there is a user namespace, but it is not used by default when we spin up a default container. So if you don't have such a namespace, then the user that you use inside a container is the same user that you have on the host machine. And one final namespace that I want to talk about is called cgroup. Okay, I know cgroup is different concept in Linux, but there is also a namespace called cgroup. What the cgroup allows us to do is, it allows container from seeing that it is limited by cgroup. So to understand this namespace, let's first look at what cgroup means. Cgroup is basically like a resource manager or resource controller. When you have multiple containers running, we don't want those containers to use all of the hardware resources available, right? We want to provide some restriction so one container won't clog up, hog the hardware available and star other containers or host operating system. And this is enabled using this Linux primitive called cgroup. With cgroup, what we can say is when a container is starting, we can say that this container can only use say 1 GB of memory, and it can only use these many CPU, and it can only access these many or these type of IO devices. We'll be able to do all of those with the cgroup, and that cgroup is basically a file. Okay, we define these restrictions in a file, and we assign that to a container. What that means is that restriction applies to the container that are part of that cgroup. We can also assign multiple containers to the same cgroup. In that case, if we have 1 GB limitation, then that 1 GB limitation on RAM, then that 1 GB is shared among all the containers assigned to the same cgroup. It is not that they each get 1 GB. This is actually limitation defined at cgroup level, and any process assigned to that particular cgroup will share that limitation. Okay, so that is something to remember. So basically, cgroup defines what is the allowance of hardware for this particular process within a container. Now, obviously, we don't want containers to know that they are actually restricted by cgroup. They are actually running inside a container. We don't want a process running inside a container to know that they are running inside a container and they are restricted by cgroup. And to provide that isolation, we use cgroup namespace. When we have cgroup namespace created and assigned, it will not be, the process running within the container will not be able to see that they are actually restricted by or limited by cgroups. So that is another level of isolation. So if we go back, we have process level isolation using PID namespace and file system level isolation using mount namespace. Then we have net namespace to provide container's own network, UTS namespace to define the host name for the container, IPC namespace to enable interprocess communication among the process within a container, but at the same time restrict them being accessing any shared memory or message queues to communicate with other processes in the host operating system or in other containers. And we have user namespace, not enabled by default, but if it is enabled, we'll be able to map a user from container to some other user in the host. And then we also have cgroup namespace isolation. This allows containers, this basically ensures process running within a container doesn't know that they are restricted by cgroups or doesn't know that they are running within a container. And we also saw that we have cgroups. Cgroups are basically like a resource manager. It allocates how much hardware each of the container or process within a container can use. So basically that's it. The combination of namespaces and cgroups provides the isolation that we need for the container without creating an entire guest operating system. Okay, as you can see, this is just some magic done by Linux rather than running another operating system on top of another operating system. Okay, so this is why containers are lightweight, while providing guest operating system level of isolation. It is not exactly same, but it provides, or it gets very close to what we can do with guest operating system. Okay, so this is why container isolation is very powerful and popular, lightweight. That is all I wanted to talk about in this video. I hope this is useful. Thank you.